Good evening. Welcome to this event of the Cosmic Zoom exhibition. As most of you must know by now, Cosmic Zoom is a virtual exhibition that was curated by the ICTS, and it aims to take all of you through a journey across the scales of cosmos, starting from the smallest to the largest, smallest subatomic particles, and taking all the way to the edge of the observable universe. So if you haven't already taken this journey, I encourage all of you to take this journey. And the website is given here. It's cosmic-zoom.in. We are also organizing several events as part of this exhibition until April 18. And these events are listed on the Cosmic Zoom webpage. So it's cosmiczoom.in/events. There is the Cosmic Zoom is also on various social media platforms, including Facebook, Twitter, and Instagram. So I encourage you to follow and like us, etc. And today, I'm very pleased and glad to present today's speaker, Mr. R Madhusudan from the Jawaharlal Nehru Planetarium, Bengaluru. Mr. Madhusudan is an educator and a wonderful teacher. He has been working at the planetarium since 1995. He's almost one of the founding members of the planetarium. He was worked very, very closely with the founding director of the planetarium, Professor C.V. Vishweshwara. And he is involved in several aspects of the planetarium, including teaching and organizing various academic programs to the planetarium. He has taught several generations of the students, of Bangalore students, to various programs at the planetarium. He is also involved in the production of various planetarium shows. Last year, under the leadership of Mr. Madhusudan, they have recreated one of the classic shows that was curated by Professor Vishweshwara, I don't know, 2 decades ago. And I know that now he is working on another very exciting show on gravity, which we all are waiting to see. So today, I'm very pleased to introduce and welcome Mr. Madhusudan, and he'll be talking about solar system as a laboratory for fundamental physics. This talk will be in English as well as in Kannada. So you are very welcome to ask questions both in English and Kannada. And if you do not know one of the languages, please be patient. And while he explains it in the other language, he will be sure to come back and explain in the other language. So with this introduction, let me welcome Mr. Madhusudan.
Thank you very much. I'll just share my screen. Okay, so is my slide, first slide, clearly visible?
Yes.
Okay. So thank you very much, Professor Ajit. It's really overwhelming to hear things that you said about me, and it is an equal pleasure to be part of a program that you are in. So you were also part of that program you mentioned about planetarium show some time back, and you have been helping us the current one as well. So thank you very much for all that, and I would like to thank you for this opportunity to make a small presentation about a topic which is very close to me. So for the rest of the people who are out there, I must admit that I'm not a subject expert. I'm not an astronomer, and I'm very glad that Professor Ajit introduced me as a teacher. So that's how I see myself. And whatever I read, understand, and I feel excited about, I feel very happy to share the same with the rest of the community. So it is in that spirit that I have prepared this particular presentation, not as a subject expert, but as somebody who has been excited about some aspect of solar system. And that's what I would like to present before you. ಈ ಕಾರ್ಯಕ್ರಮದಲ್ಲಿ ಕನ್ನಡ ಮತ್ತು ಇಂಗ್ಲಿಷ್ ಎರಡರಲ್ಲೂ ಪ್ರತಿಯೊಂದು ವಾಕ್ಯವನ್ನು ನಾವು ಇಂಗ್ಲಿಷ್ ಮತ್ತು ಕನ್ನಡದಲ್ಲಿ ಎರಡೂ ಹೇಳೋದಕ್ಕೆ ಕಷ್ಟ ಆಗುತ್ತೆ. ಸೊ ಇಲ್ಲಿ ಏನು ಮಾಡ್ತೀನಿ ಅಂತ ಹೇಳಿದ್ರೆ, ಇಂಗ್ಲಿಷು ಮತ್ತು ಕನ್ನಡದಲ್ಲಿ ಹೇಳುವಾಗ ಬಹಳಷ್ಟು ಮುಖ್ಯವಾಗಿರುವಂಥ ಅಂಶಗಳನ್ನು ನಾನು ಕನ್ನಡದಲ್ಲಿ ಮತ್ತೆ ಮನನ ಮಾಡಿಕೊಂಡು ಅದನ್ನು ಇಂಗ್ಲಿಷ್ನಲ್ಲಿ ಮುಂದುವರಿಸ್ಕೊಂಡು ಹೋಗ್ತೀನಿ. ಸೊ it will be a bilingual presentation, and it's very challenging to make a bilingual presentation because you do get carried away in one language or the other as you are presenting, and I hope that I will be able to strike a balance between the two. And so here we go. So the topic of the presentation is solar system as a test bed of physical theories. Now ಬಹಳಷ್ಟು ಭೌತಶಾಸ್ತ್ರದಲ್ಲಿ ನೋಡುವಂಥ ಯೋಚನಾವಳಿ ಏನಿದೆ, ಈ ಯೋಚನಾವಳಿಗಳಿಗೆ ಪ್ರೇರಣೆಯನ್ನ ನೀಡೋದ್ರ ಜೊತೆಗೆ ನಮ್ಮ ಸೌರವ್ಯೂಹವು ಅಲ್ಲಿ ಉದ್ಭವಿಸಿದಂಥ ಒಂದು ಬಹಳ ಪ್ರಮುಖವಾದ ಪ್ರಶ್ನೆಗಳಿಗೆ ಉತ್ತರಗಳನ್ನು ಕಂಡುಕೊಳ್ಳೋದಕ್ಕೆ ಸಾಕಾರ ಮಾಡಿಕೊಳ್ಳೋದ್ರಲ್ಲಿ ಸಾಧ್ಯ ಆಗಿದೆ. So solar system is not only something that is really an awesome entity as we see and enjoy, but it has been a laboratory for discerning astronomers. And as we shall see during the course of this presentation, there will be at least a few examples to illustrate the fact that solar system has been a wonderful laboratory, and but for this entity, many of the physical theories that we know in the realm of astronomy would have been very difficult to formulate in the first place, and verify in the second place, and in the third place to extend that to entities beyond solar system. So this is one of the important things. ನಾವೀಗ ಸೌರವ್ಯೂಹದ ಬಗ್ಗೆ ಎಷ್ಟು ತಿಳ್ಕೊಳ್ಳೋದಕ್ಕೆ ಸಾಧ್ಯ ಆಗಿದೆಯೋ, ಈ ತಿಳುವಳಿಕೆಯಿಂದ ನಾವು ಸೌರವ್ಯೂಹದಿಂದ ಆಚೆ ಇರುವಂಥ ಆಕಾಶಕಾಯಗಳ ಬಗ್ಗೆಯೂ ನಾವು ತಿಳ್ಕೊಳ್ಳೋದಕ್ಕೆ ಸಾಧ್ಯ ಆಗಿದೆ. ಹಾಗಾಗಿ ಇಲ್ಲಿ ಸೌರವ್ಯೂಹ ಅನ್ನೋದು ಒಂದು ಉಪಮಾ ತರ ನಾವು ಉಪಯೋಗಿಸ್ಕೊಳ್ಬಹುದಾಗಿದೆ. It is a metaphor for a particular system in astronomy, and we see that this particular solar system becomes a metaphor, and we can extend whatever we have learned, whatever we have discovered in the context of solar system work equally well beyond the solar system. So truly, to take the physical theories from the boundaries of the earth to the realm of cosmos, the first ladder where we test our physical theories has been the solar system. ಈ ಒಂದು ಪ್ರೆಸೆಂಟೇಷನ್ ಅನ್ನು ನಾನು ಮುಂದುವರಿಸೋದಕ್ಕೆ ಮುಂಚೆ ಒಂದು ವೈಯಕ್ತಿಕವಾದ ವಿಷಯವನ್ನ ಹಂಚಿಕೊಳ್ಬೇಕಾಗತ್ತೆ. This is a very personal as well as professional piece of information that I would like to share before I continue with my presentation. I hope that I am not digressing too much by way of introducing this. Very recently, on the 3rd of April, an eminent entomologist, Professor K. Chandrasekhara of University of Agricultural Sciences, passed away. It's really saddening to inform. Especially, he was very close to the planetarium academic activities. He was part of all the academic programs of the planetarium. He was a regular teacher in several of the planetarium academic programs. He inspired a large number of students here to take to research. So even though he was an entomologist and he came from a pure biological discipline, his interest in other scientific disciplines were no less. And he encouraged even students of physics to take to biology and vice versa. And it's very sad that we lost him, and especially planetarium is saddened to know that he will not be around when we plan an academic program the next time. He was a permanent faculty who came to teach here over the last 20-22 years, and we will be really missing him, Professor K. Chandrasekhara. There is another reason why I should be mentioning him right at the beginning. While I was preparing for this particular talk, one of the books that I used profusely was Archives of the Universe. And this book was gifted to me by Professor Chandrasekhara some 10 years back. And it is a great coincidence that I was reading these chapters from that book when I heard the sad news that he is no more. So Professor K. Chandrasekhara ಅವರಿಗೆ ಈ ಮೂಲಕ ಒಂದು ವೈಯಕ್ತಿಕವಾಗಿ ಹಾಗೂ ನನ್ನ ಸಂಸ್ಥೆಯ ಪರವಾಗಿ ಒಂದು ಶ್ರದ್ಧಾಂಜಲಿಯನ್ನ ಅರ್ಪಿಸೋದಕ್ಕೆ ಅನುಮತಿ ಇದೆ ಅಂತ ಅನ್ಕೊಂಡಿದ್ದೀನಿ. We will miss him very badly. But I don't want to sound a melancholic note right at the beginning, so let us get started now. Even Professor Chandrasekhar would not have allowed this. Okay, so let us come to the topic straight away. So astronomy is essentially an observational science, and it is not an experimental science. ಇಲ್ಲಿನ ಖಗೋಳ ವಿಜ್ಞಾನದಲ್ಲಿ ಏನಂತ ಹೇಳಿದ್ರೆ ಬಹಳಷ್ಟು ಮಟ್ಟಿಗೆ ನಾವು ವೀಕ್ಷಣೆಗಳಿಗೆ ಇಲ್ಲಿ ಹೆಚ್ಚು ಒತ್ತನ್ನ ಕೊಡ್ತೀವಿ. ಇದು ಪ್ರಾಯೋಗಿಕವಾಗಿ ಮಾಡೋದಕ್ಕೆ ಇಲ್ಲಿ ಬಹಳ ಕಡಿಮೆ ಅವಕಾಶಗಳಿರುತ್ತೆ. ಈಗ ಎಷ್ಟೋ ಜನ ಖಗೋಳ ವಿಜ್ಞಾನಿಗಳು ಇದನ್ನ ನೋಡಿದ ತಕ್ಷಣ ಇದು ಎಕ್ಸ್ಪೆರಿಮೆಂಟಲ್ ಸೈನ್ಸ್ ಅಲ್ಲ ಅಂತ ಹೇಳಿದ್ರೆ ತಪ್ಪಾಗಿ ತಿಳ್ಕೊಳ್ಬಹುದು. ಸೊ ಲೆಟ್ ಮಿ ಕ್ಲಾರಿಫೈ ರೈಟ್ ಅಟ್ ದ ಬಿಗಿನಿಂಗ್ ದಟ್ ವಾಟ್ ಐ ಮೀನ್ ಬೈ ಎಕ್ಸ್ಪೆರಿಮೆಂಟಲ್ ಸೈನ್ಸ್ ಆರ್ ವೈ astronomy is not an experimental science in the real sense. See, we are used to doing experiments in the laboratory, either in physics or chemistry or biology. And in all these experiments, you have a number of parameters which have a bearing on the result of the experiment. And in the tabletop experiment, like the one you see here on the right-hand side, I'll play the video very shortly. You have control over all the parameters that go into this experiment. Therefore, you can control various things. And in that sense, astronomy is not an experimental science. You cannot arrange planets according to your choice. ನಿಮಗೆ ಬೇರೆ ಬೇರೆ ಗ್ರಹಗಳು ಯಾವ ಯಾವ ದೂರದಲ್ಲಿ ಇದೆಯೋ ಅವುಗಳ ದೂರವನ್ನು ನಾವು ವ್ಯತ್ಯಾಸ ಮಾಡೋದಕ್ಕೆ ಸಾಧ್ಯ ಆಗೋದಿಲ್ಲ. ಅಥವಾ ಯಾವುದೇ ಒಂದು ಗ್ರಹದ ಒಂದು ದ್ರವ್ಯರಾಶಿ ಎಷ್ಟಿದೆಯೋ ಅದರಲ್ಲಿ ಅರ್ಧ ಪಟ್ಟು ಹೆಚ್ಚು ಕಡಿಮೆ ಮಾಡಿದಾಗ ನಾನು ಇದು ಯಾವ ರೀತಿಯಾದಂಥ ಪರಿಣಾಮ ಬೀರುತ್ತೆ ಅಂತ ನಾನು ಕಂಡುಕೊಳ್ಬೇಕಾದ್ರೆ ಅದು ಸಾಧ್ಯ ಆಗೋದಿಲ್ಲ. It's difficult to alter the mass or the distance of a planet to see what effect that would have, say, on the period of revolution around the sun. Whereas in an experiment like this is a typical experiment. So let us first watch the video. So there is somebody who is dropping hydrochloric acid into a container with sodium thiosulfate. The transmitted light actually takes different hues. There are different colors as the time goes by. ಸೊ ಸಮಯ ಹೋಗ್ತಾ ಇದ್ದ ಹಾಗೇನೆ ಅಲ್ಲಿ ಒಂದು ಗ್ಲಾಸ್ ಕಂಟೈನರ್ ಏನಿತ್ತು ಅದರ ಮೂಲಕ ಆದಂತ ಬೆಳಕು ಅದರ ಬಣ್ಣದಲ್ಲಿ ವ್ಯತ್ಯಾಸ ಆಗೋದನ್ನ ನಾವು ಕಂಡ್ವಿ. ಈ ಬಣ್ಣ ಯಾವ ದರದಲ್ಲಿ ವ್ಯತ್ಯಾಸ ಆಗ್ತಾ ಇದೆ ಅಥವಾ ಯಾವ ಬಣ್ಣಕ್ಕೆ ಮಾತ್ರ ಅದು ನಾವು ಯಾವ ಬಣ್ಣಗಳನ್ನ ಮಾತ್ರ ನಾವು ನೋಡೋದಕ್ಕೆ ಸಾಧ್ಯ, ಇದನ್ನ ನೋಡ್ಬೇಕಾದ್ರೆ ನಮಗೆ ಈ ಒಂದು ಪ್ರಯೋಗದಲ್ಲಿ ಪೂರ್ಣ ಕಂಟ್ರೋಲ್ ಇರುತ್ತೆ. ಸೊ ವಿ ಕ್ಯಾನ್ alter the concentration of hydrochloric acid, we can alter the concentration of sodium thiosulfate, we can change the source of light. Thereby we can see the effect of each of these parameters on the final result that we observe, so that we know the relative role of each of these parameters on the transmitted the color of the transmitted light. Now you can't do this in an astronomical system. You can't change masses, you can't change distances, you can't change their orientations. You have to live with the way nature has created, and you have just one system to study for each of these problems. As a result, astronomy is not considered as an experimental science in this sense. But there are many experiments that are done, but not the way that we usually do in a physics lab or a chemistry lab or a biology lab. Now we shall see how solar system has been able to yield itself to the experiments and observations that people have done over the last 3.5 centuries. And because of that, the wealth of information the kind of principles, the kind of theories, physical theories that have come out of these activities is tremendous. And they have impacted not just our study of solar system, it has impacted our study of cosmology in general. So solar system becomes a metaphor, as I mentioned right at the beginning. ಈಗ ಮೊದಲ ಉದಾಹರಣೆಗೆ ಇಲ್ಲಿ ಇದು ಚಂದ್ರಗ್ರಹಣದ ಒಂದು ಫೋಟೋಗ್ರಾಫ್ ಇದು. ಸೊ ಈ ಛಾಯಾಚಿತ್ರದಲ್ಲಿ ನೀವು ನೋಡ್ತಾ ಇರೋದೇನಪ್ಪ ಅಂತ ಹೇಳಿದ್ರೆ, ಭೂಮಿಯ ನೆರಳು ಚಂದ್ರನ ಮೇಲೆ ಬೇರೆ ಬೇರೆ ಸಮಯದಲ್ಲಿ ಒಂದೇ ಗ್ರಹಣದ ಕಾಲದಲ್ಲಿ ಬಿದ್ದಾಗ ಯಾವ ರೀತಿ ಇರುತ್ತೆ ಅಂತ ಹೇಳಿ. ಸೊ ವಿ ಸಿ ದ ಶೇಪ್ ಆಫ್ ದ ಶಾಡೋ ಆಫ್ ದ ಅರ್ತ್ ಆನ್ ದ ಮೂನ್ during the different times of a particular lunar eclipse. So you find that the collage of all this gives you a circular shape of the shadow. In fact, if you were to carry out this experiment at different lunar eclipses and you study the shape of the Earth's shadow falling on the moon, you'll find that it is always part of a circle. And that is exactly what Aryabhatta the first found several centuries back, around 6th century to be precise. So what can we conclude from this? So he concluded from this that no matter what the orientation of the Earth in space is, if the shadow of the Earth is always a part of a circle when it is projected on the surface of the moon, then it is very reasonable to conclude that the shape of the Earth must be that of a sphere. ಭೂಮಿ ಗೋಳಾಕಾರದಲ್ಲಿದೆ ಅನ್ನೋದಕ್ಕೆ ಇದು ಒಂದು ಪುರಾವೆಯನ್ನ ನೀಡಿತು. ಆರ್ಯಭಟ ಇದನ್ನ ಬಹಳ ತಾರ್ಕಿಕವಾಗಿ ಜೊಮೆಟ್ರಿಯ ಮೂಲಕ, ಜ್ಯಾಮಿತಿಯ ಮೂಲಕ ಇದನ್ನ ಲೆಕ್ಕಾಚಾರ ಮಾಡಿ ಭೂಮಿಯ ಆಕಾರ ಏನಿದೆ ಅದು ಗೋಳಾಕಾರವಾಗಿದೆ ಅಂತ ಹೇಳಿ ತೋರಿಸ್ಕೊಟ್ರು. ಸೊ ವಿ ಸಿ ದಟ್ ಇವನ್ ಲಾಂಗ್ ಎಗೋ a solar system object has been able to throw light on the shape of the Earth. And later on, if possible, we may be able to elaborate on this. Knowing the shape of the Earth is extremely important. The shape and size of the Earth, that forms the basic knowledge on which the rest of the astronomy is built upon. Now, when we talk about the solar system, first of all, the word system catches our attention. ಇದು ಸೌರವ್ಯೂಹ. ಈ ಸೌರವ್ಯೂಹದಲ್ಲಿ ಬಹಳಷ್ಟು ಆಕಾಶ ಕಾಯಗಳಿರುತ್ತೆ. ಈ ಆಕಾಶ ಕಾಯಗಳೆಲ್ಲಾನು ಚದುರಿ ಹೋಗಿರೋದಿಲ್ಲ. ಅದು ಯಾವುದೋ ಒಂದು ರೀತಿಯಲ್ಲಿ ಬಂಧಿತವಾಗಿದೆ ಅಂತ ನಾವು ಹೇಳ್ಬೋದು. So we can say that this is not merely a random collection of objects which actually gives rise to a solar system. There is a certain kind of relationship among the different components of the solar system objects. So you may have the sun, the planets, the comets, and so many other objects. Now all these objects have some kind of common thread running through them, because of which they form a system. And secondly, you would like to ask, how big is the solar system? So first of all, what forms this system? And secondly, how big is the solar system? Now, this particular question is a perfectly scientific question. Whether you are studying something as big as the solar system, or you are studying something as small as an atom is also a system by itself, because there are different components that go into make an atom. Now you would like to ask, what are the different components of an atom? How are all these components held together? How big is an atom? Why is an atom stable? So why does it not disintegrate as soon as it is formed? So these are all perfectly scientific questions you ask about any system. And the solar system is no exception. Therefore, people have been asking questions for the last few thousand years, these questions. And it is only in recent times that we have found, or we seem to have found answers to many of these questions. ಅಂದ್ರೆ ಸೌರವ್ಯೂಹದ ವ್ಯಾಪ್ತಿ ಎಷ್ಟಿದೆ, ಸೌರವ್ಯೂಹದಲ್ಲಿ ಯಾವ ರೀತಿಯಾದಂತಹ ಕಾಯಗಳಿವೆ, ಈ ಕಾಯಗಳನ್ನೆಲ್ಲ ಹಿಡಿದಿಟ್ಟಿರುವಂತಹ ಒಂದು ಶಕ್ತಿ ಯಾವುದು, ಈ ಶಕ್ತಿಯ ಮೂಲ ಏನು, ಈ ಶಕ್ತಿಯ ಮೂಲ ಸ್ವರೂಪ ಏನಿದೆ, ಮತ್ತೆ ಇದು ಬಹಳಷ್ಟು ವರ್ಷಗಳಿಂದ, ಈಗ ನಮಗೆ ತಿಳಿದಿರೋ ಹಾಗೆ ಸೌರವ್ಯೂಹ ಸುಮಾರು 4.5 ಬಿಲಿಯನ್ ವರ್ಷಗಳಿಂದ ಇದೆ. ಇಷ್ಟು ದೀರ್ಘಕಾಲದಲ್ಲಿ ಅದು ಒಂದೇ ತರದಲ್ಲಿ ಇದೆ ಅಂತ ಹೇಳಿದ್ರೆ ಇದಕ್ಕೆ ಕಾರಣ ಏನು? ಸೊ ಈ ತರ ಪ್ರಶ್ನೆಗಳಿಗೆ ಈ ತರ ಪ್ರಶ್ನೆಗಳನ್ನ ಖಗೋಳ ವಿಜ್ಞಾನಿಗಳು ಆಗಿಂದಾಗೆ ಹಾಕೊಳ್ತಾ ಬಂದಿದ್ದಾರೆ. ಇಂತಹ ಪ್ರಶ್ನೆಗಳಿಗೆ ಉತ್ತರವನ್ನ ನಾವು ಕಂಡ್ಕೊಳ್ಳೋದಕ್ಕೆ ಸಾಧ್ಯ ಆಗಿರೋದು ಇತ್ತೀಚಿನ ವರ್ಷಗಳಲ್ಲಿ ಅಷ್ಟೇನೆ. That is mainly because we have been able to understand what is happening in the solar system, and we have come up with certain interesting methodology of studying them. So the rest of the presentation will be about these questions and how we have been able to answer them. The solar system. So what is solar system? So there it is on the screen. According to Ptolemy, the solar system was arranged like this. This arrangement is very important because that was according to Ptolemy, Earth was at the center, followed by the moon, then Mercury, Venus, and then the sun. And you have planet, the most distant planet, the Saturn. So all these planets were supposed to be going around the Earth, and that was the geocentric model. So ಭೂಕೇಂದ್ರ ವಾದದಲ್ಲಿ ಟಾಲಮಿಯ ಪ್ರಕಾರ ಇರುವಂತಹ ಈ ಭೂಕೇಂದ್ರ ವಾದದಲ್ಲಿ ಭೂಮಿ ಕೇಂದ್ರದಲ್ಲಿರುತ್ತೆ. ಭೂಮಿಯ ಸುತ್ತ ಈ ಎಲ್ಲಾ ಗ್ರಹಗಳು ಮತ್ತೆ ಸೂರ್ಯ ಚಲಿಸ್ತಾ ಇರುತ್ತೆ. ಮತ್ತೆ ದೂರದಲ್ಲಿರುವಂತಹ ನಕ್ಷತ್ರಗಳಿಗೆ ಯಾವುದೇ ರೀತಿಯಾದಂತ ಚಲನೆ ಇರೋದಿಲ್ಲ. ಸೊ ದೇ ಆರ್ ಕಾಲ್ಡ್ ಫಿಕ್ಸ್ಡ್ ಸ್ಟಾರ್ಸ್ ಬಿಕಾಸ್ ದೀಸ್ ಸ್ಟಾರ್ಸ್ did not seem to have any proper motion like planets. Now this is the most natural model that you can think about, because if you look up at the sky today, you will see that all these objects rise in the east and set in the west, no exception. Therefore it is very natural to think that Earth is the center and everything goes around us. Now the important thing is that the real arrangement of planets out there in the sky? So if you were to leave the Earth and you were to observe these motions, then would you see all of them going around the Earth? That is a question. But then in Ptolemy's time, the most important thing was to have an arrangement like this, which could describe the observed motion of the planets. So ಗ್ರಹಗಳ ಚಲನೆಗಳೇನಿರುತ್ತೆ, ಈ ಗ್ರಹಗಳ ಚಲನೆಗಳನ್ನ ನಾವು ಯಾವ ರೀತಿಯಾದಂತ ಒಂದು ಮಾದರಿಯ ಮೂಲಕ ಅರ್ಥ ಮಾಡ್ಕೊಳ್ಳೋದಕ್ಕೆ ಸಾಧ್ಯನೋ ಆ ತರದ ಒಂದು ಮಾದರಿಯನ್ನ ಇಲ್ಲಿ ತಯಾರು ಮಾಡಿದ್ರು. ಈ ಮಾದರಿಯ ಪ್ರಕಾರ ಬೇರೆ ಬೇರೆ ಗ್ರಹಗಳು ಯಾವ ರೀತಿ ಚಲಿಸ್ತಾ ಇದ್ವು ಅನ್ನೋದನ್ನ ಅರ್ಥ ಮಾಡ್ಕೊಳ್ಳೋದಕ್ಕೆ ಬಹಳ ಸುಲಭವಾಗಿ ಇಲ್ಲದೆ ಹೋದ್ರೂ ಅರ್ಥ ಮಾಡ್ಕೊಳ್ಳೋದಕ್ಕೆ ಸಾಧ್ಯ ಆಯ್ತು. So it was a complex model, but still it was a model that worked because they could describe the observed motions. Now one of the observed motions of planets, especially of planet Mars, is what is known as a retrograde motion. So as you can see in this particular picture, this is a photograph of, this is actually a simulation, but you can get a photograph of this kind if you could take the photograph of planet Mars on different dates. So planet Mars seems to be moving in a particular direction as my mouse pointer is moving. And then it seems for some strange reason to slow down and then halt and then make a turn. So it goes back. It goes back for some months, and then it again slows down and reverses and starts moving in the original direction that it was. So these constellations in the background help you to determine the direction in which planet Mars is moving. So ಯಾವುದೋ ಒಂದು ಡೈರೆಕ್ಷನ್ ಅಲ್ಲಿ ಹೋಗ್ತಾ ಇರೋದು ಅದು ಮತ್ತೆ ವಾಪಸ್ ಬಂದು ಇನ್ನೊಂದ್ಸಲ ವಾಪಸ್ ಹೋಗಿ ಅದು ಮೂಲತಃ ಯಾವ ದಿಕ್ಕಿನಲ್ಲಿ ಚಲಿಸ್ತಾ ಇತ್ತು ಅದೇ ದಿಕ್ಕಿನಲ್ಲಿ ಚಲಿಸೋ ಹಾಗೆ ಇದನ್ನ ವೀಕ್ಷಣೆ ಮಾಡಿದ್ರು. This is a very complex motion actually. It's very, very hard. Therefore, the model that Ptolemy came up with also was equally complex. ಇದರ ಪ್ರಕಾರ ಏನ್ ಮಾಡಿದ್ರು ಅಂತ ಹೇಳಿದ್ರೆ, the planet actually did not move in a circular path around the Earth. Okay, the planet actually moved in a small circle that you see on top, which is called the epicycle, and the center of this epicycle was actually going in a circular path around the Earth. So if you look at the big circular path, there is no object actually involved with that particular circle. The actual object is moving in a small circle at the top, and the center of that small circle is what is moving in the circular path. Now, at the bottom left, right of the screen, ನಿಮ್ಮ ಸ್ಕ್ರೀನಿನ ಕೆಳಗಡೆ ಬಲಭಾಗದಲ್ಲಿ ಇದೆಯಲ್ಲ, ಇದ್ರ ಪ್ರಕಾರ ಏನಾಗುತ್ತೆ ಅಂತ ಹೇಳಿದ್ರೆ, ಈ ಸಣ್ಣ ವೃತ್ತದ ಮೇಲೆ ಈ ಗ್ರಹ ಚಲಿಸ್ತಾ ಇದ್ದು, ಈ ಸಣ್ಣ ವೃತ್ತದ ಕೇಂದ್ರ ಇದೆಯಲ್ಲ, ಅದು ದೊಡ್ಡ ವೃತ್ತದ ಒಂದು ಸರ್ಕಂಫರೆನ್ಸ್ ಮೇಲೆ ಹೋಗ್ತಾ ಇರೋವಾಗ ಏನಾಗುತ್ತೆ ಅಂತ ಹೇಳಿದ್ರೆ, ಅದು ನಾವು ಈ ಹಿಂದಿನ ಪಿಕ್ಚರ್ ಅಲ್ಲಿ ನೋಡಿದ್ವಲ್ಲ, ಒಂದು ದಿಕ್ಕಿನಲ್ಲಿ ಚಲಿಸ್ತಾ ಇರುವಂತಹ ಗ್ರಹ ಅದು ಹೇಗೆ ಹಿಮ್ಮುಖ ಚಲನೆಯನ್ನ ತೋರಿಸುತ್ತೆ ಅಂತ ಹೇಳಿ, ಆ ಹಿಮ್ಮುಖ ಚಲನೆಯನ್ನ ನಾವು ಈ ಒಂದು ಮಾದರಿಯ ಮುಖಾಂತರ ಅರ್ಥ ಮಾಡ್ಕೊಳ್ಳೋದಕ್ಕೆ ಸಾಧ್ಯ ಆಯಿತು. So it was possible to understand retrograde motion by having these epicycles which are moving on a big circle. It's really complicated. So if we were to draw the orbits of all the planets and to account for the observed number of retrograde motions of different planets, you would have something which is really complicated like this. So the model is complicated, the motion that you are trying to understand is complicated, and in spite of this complication, this model was accepted for almost 1,500 years, and people were happy with this. ಇದಕ್ಕೆ ಬದಲಾಗಿ ನಮಗೆ ಇನ್ನೊಂದು ಮಾದರಿ ಇಲ್ಲದೆ ಇರೋದ್ರಿಂದ ಈ ಮಾದರಿ ಎಷ್ಟೇ ಕ್ಲಿಷ್ಟಕರವಾಗಿದೆ ಅಂತ ಅನ್ಸಿದ್ರು ಕೂಡ ಈ ಕ್ಲಿಷ್ಟಕರವಾದ ಮಾದರಿಯಿಂದ ನಾವು ಯಾವುದೇ ಒಂದು ಗ್ರಹ 100 ವರ್ಷನೋ 200 ವರ್ಷನೋ ಹಿಂದಿನ ಕಾಲ ಸಮಯದಲ್ಲಿ ಅದು ಆಕಾಶದಲ್ಲಿ ಎಲ್ಲಿ ಇರ್ತಿತ್ತು ಅಂತ ನಾವು ನಿಖರವಾಗಿ ಹೇಳೋದಕ್ಕೆ ಸಾಧ್ಯ ಆಗ್ತಿತ್ತು. ಅದೇ ರೀತಿ 50 ವರ್ಷನೋ 100 ವರ್ಷನೋ ಮುಂದೆ ಯಾವುದೋ ಒಂದು ಗ್ರಹದ ಒಂದು ಪೊಸಿಷನ್ ನಮಗೆ ತಿಳಿಬೇಕಾದ್ರೆ ಇದನ್ನ ಈ ಮಾದರಿನ ಉಪಯೋಗಿಸಿಕೊಂಡು ಹೇಳೋದಕ್ಕೆ ಸಾಧ್ಯ ಆಗ್ತಿತ್ತು. So we could predict the past positions of a given planet and predict the future positions of a particular planet using this complicated model, and that's the reason why it survived in spite of its complexity. But it all changed with Copernicus coming there around 16th century, 15th century. He replaced the center of the Ptolemy's model, where there was Earth. Now he replaced it with Sun. So Ptolemyಯ ಮಾದರಿಯಲ್ಲಿ ಅದು ಕೇಂದ್ರದಲ್ಲಿ ಭೂಮಿ ಇತ್ತು. ಈಗ ಆ ಭೂಮಿಯ ಜಾಗದಲ್ಲಿ ಸೂರ್ಯನನ್ನ ಕೇಂದ್ರದಲ್ಲಿಟ್ಟು ಬೇರೆ ಗ್ರಹಗಳೆಲ್ಲ ಸೂರ್ಯನ ಸುತ್ತುವಂತ ಒಂದು ಮಾದರಿಯನ್ನ ಕೊಪರ್ನಿಕಸ್ ಕೊಟ್ರು. ಈ ಮಾದರಿ ಮುಖಾಂತರ ನಾವು ಈ ಮಾದರಿಯನ್ನ ನಾವು ಟಾಲಮಿಯ ಮಾದರಿಯ ಜೊತೆಗೆ ಹೋಲಿಸಿದ್ರೆ ಇದು ನೋಡೋದಕ್ಕೆ ಬಹಳ ಸರಳವಾಗಿದೆ ಅಂತ ಅನ್ಸುತ್ತೆ. It looks like it is much simpler model than what was proposed by Ptolemy. But even this was not without its epicycles. Small epicycles were retained by him. But this is basically to account for something else and not the retrograde motion. Therefore, Copernican model is also as less complicated than Ptolemy's, but still complicated, not very simple as the textbooks would tell you. But the interesting thing is both the models had similar kind of errors or similar kind of precision, if you like, in predicting the positions of planets in the past or position of the planets in future. ಇದು ಟಾಲಮಿ ಮಾದರಿ ಅಷ್ಟೇ ಇದು ನಿಖರವಾಗಿದ್ರೆ ಟಾಲಮಿಯ ಮಾದರಿಯನ್ನ ನಾವು ಯಾವ ಕಾರಣಕ್ಕೋಸ್ಕರ ಕೊಪರ್ನಿಕಸ್ ಮಾದರಿಯಿಂದ ನಾವು ರೀಪ್ಲೇಸ್ ಮಾಡಬೇಕಾಗಿ ಬರುತ್ತೆ. There is no reason for that at all. Why we should replace Ptolemy's model with Copernican model if Copernican model is only as good as Ptolemy's model? Adre, one thing that we see here is that any new model often comes with new conclusions. It leads to new conclusions. ಹೊಸ ವಿಚಾರಗಳನ್ನ ನಾವು ಈ ಹೊಸ ಮಾದರಿಯ ಮೂಲಕ ತಿಳ್ಕೊಳ್ಳೋದಕ್ಕೆ ಸಾಧ್ಯ ಆಗುತ್ತೆ. Now, what this Copernican model did, which Ptolemaic model did not do, was to show that there is a particular orderliness in the arrangement of planets. In the Ptolemy's model, you could actually have planets at any distance from the sun, any distance from the Earth, and these planets could be in any order. So the nearest need not be Mercury, the farthest need not be Saturn. You could put it in any order, and you just have to adjust the size of the two circles, one big circle and a small epicycle. And there is a little bit of geometrical adjustment that one had to do. And with these adjustments, it was possible to show that it was possible to describe the motion of any planet, no matter where it was. But that was not the case with the Copernican model. In Copernican model, the position of planets, the distance of planets from the sun became fixed. And this is a very big idea that is not there in Ptolemaic model. So it gives you some ways to estimate distances because the order of the planets are fixed. Now, once you do this, then you have partly answered the question, how big is the solar system, right? So Copernican model was better in many aspects compared to the Ptolemaic model. And these are the distances that Copernican model allowed. Copernicus himself has prepared this kind of a table. And then we also have this modern value from today's. So you see that there is a very good agreement between the distances to planets from the sun that were computed by Copernicus and what has been computed in modern astronomy. So the match is very, very good. So this is one of the great things about a new theory, a great theory. It gives you some information which is not there in the old theory. But a great theory should also make some prediction of some unobserved phenomena. ಅಂದ್ರೆ ನಾವು ಬರಿಗಣ್ಣಿನಿಂದ ಏನೆಲ್ಲ ನಾವು ವೀಕ್ಷಿಸಿರ್ತೀವಿ, ಈ ವೀಕ್ಷಣೆಗಳನ್ನ ನಾವು ವಿವರಿಸೋ ಒಂದು ಕಾರಣಕ್ಕೋಸ್ಕರ ಒಂದು ಮಾದರಿಯನ್ನ ತಯಾರು ಮಾಡಿರ್ತೀವಿ. ಆದರೆ ಯಾವುದೇ ಒಂದು ಒಳ್ಳೆ ಮಾದರಿ ಅಥವಾ ಒಂದು ಅತ್ಯುನ್ನತ ಮಾದರಿ ಅಂತ ಹೇಳಿದ್ರೆ, ಈ ಮಾದರಿಯನ್ನ ಉಪಯೋಗಿಸ್ಕೊಂಡು ನಾವು ಏನನ್ನ ವೀಕ್ಷಿಸಿಲ್ಲವೋ ಅಥವಾ ಏನು ನಮ್ಮ ಬರಿಗಣ್ಣಿನಿಂದ ವೀಕ್ಷಣೆ ಮಾಡೋದಕ್ಕೆ ಸಾಧ್ಯ ಇಲ್ಲವೋ ಅಂತಹ ವಿದ್ಯಮಾನಗಳನ್ನ ಇದು ಮುಂಚಿತವಾಗಿ ನಮಗೆ ತಿಳಿಸೋ ಹಾಗಿರಬೇಕು. Therefore, one of the great characteristics of a great theory is that it should predict something that we have not seen. So what did Copernican theory do? So Copernicus said, if one could improve the power of vision, one will see phases of planet Venus, and it will appear biggest when in the crescent phase. ಈಗ ಚಂದ್ರನ ಕಲೆಗಳನ್ನ ನಾವು ನೋಡ್ತೀವಲ್ಲ, ಆ ಚಂದ್ರನ ಕಲೆಗಳ ಹಾಗೇನೆ ಶುಕ್ರ ಗ್ರಹದಲ್ಲೂ ನಾವು ಪೂರ್ಣ ಶುಕ್ರ ಗ್ರಹವನ್ನ ನೋಡ್ತೀವಿ ಅಥವಾ ಭಾಗಶಃ ಶುಕ್ರ ಗ್ರಹವನ್ನ ನೋಡ್ತೀವಿ. ಬಾಲಚಂದ್ರವನ್ನ ನಾವು ಹೇಗೆ ನೋಡ್ತೀವೋ ಅದೇ ತರ ನಾವು ಬಾಲ ಶುಕ್ರವನ್ನ ನೋಡ್ತೀವಿ. ಸೊ ಈ ತರ ಚಂದ್ರನಲ್ಲಿ ಕಾಣುವಂತಹ ಕಲೆಗಳನ್ನ ನಾವು ಶುಕ್ರ ಗ್ರಹದಲ್ಲೂ ಕಾಣಬಹುದು. ಆದರೆ ಒಂದು ವ್ಯತ್ಯಾಸ ಏನಪ್ಪಾ ಅಂತ ಹೇಳಿದ್ರೆ, ನಾವು ಬಾಲ ಶುಕ್ರ ಗ್ರಹವನ್ನ ನೋಡಿದಾಗ ಅದು ನಮಗೆ ಅತ್ಯಂತ ಸಮೀಪದಲ್ಲಿರುತ್ತೆ, ಮತ್ತೆ ಪೂರ್ಣ ಶುಕ್ರ ಗ್ರಹವನ್ನ ನೋಡಿದಾಗ ಅದು ನಮ್ಮಿಂದ ಬಹಳ ದೂರದಲ್ಲಿರುತ್ತೆ. So the full Venus will always be more distant. It will be at the maximum distance from us, and the crescent Venus will be at a minimum distance from us. Now in astronomy, this distance of a celestial object also translates into what we call the angular size. ಬರಿಗಣ್ಣಿನಿಂದ ನಾವಿಲ್ಲಿ ನೋಡಿದಾಗ ಅದು ಎಷ್ಟು ದೊಡ್ಡದಾಗಿ ಒಂದು ಆಕಾಶಕಾಯ ಕಾಣುತ್ತೆ ಅನ್ನೋದು ಅದು ನಮ್ಮಿಂದ ಎಷ್ಟು ದೂರದಲ್ಲಿದೆ ಅನ್ನೋದ್ರ ಮೇಲೆ ಅವಲಂಬಿಸಿರುತ್ತೆ. ಹಾಗಾಗಿ if crescent Venus is closest to us and full Venus is farthest from us, then crescent Venus should appear very, very big compared to the full Venus. And this is a prediction that Copernicus made, and this had never been seen with the naked eye, and it is impossible to see with the naked eye. That is why he said if one could improve the power of vision, one should be able to see these phases. So there was a time when the power of human vision was actually improved, and this was due to Galileo's invention of a telescope for astronomical purposes, and it achieved what Copernicus had asked for, improve our vision. Galileo ತನ್ನ ದೂರದರ್ಶಕದ ಮೂಲಕ ಈ ಶುಕ್ರ ಗ್ರಹವನ್ನ ವೀಕ್ಷಿಸಿದಾಗ ಕೊಪರ್ನಿಕಸ್ ಯಾವ ರೀತಿಯಲ್ಲಿ ಅದರ ಗಾತ್ರದಲ್ಲಿ ಬದಲಾವಣೆ ಆಗತ್ತೆ ಅಂತ ಮುಂಚಿತವಾಗ್ಲೇ ಹೇಳಿದ್ರು, ಅದೇ ರೀತಿಯಲ್ಲಿ ಗಾತ್ರದಲ್ಲೂ ಬದಲಾವಣೆ ಆಗ್ತಾ ಇತ್ತು. ಮತ್ತೆ ಶುಕ್ರ ಗ್ರಹದ ಕಲೆಗಳನ್ನು ನಾವು ಕಾಣೋದಕ್ಕೆ ಸಾಧ್ಯ ಆಯಿತು. Exactly as Copernicus had predicted. Venus went through the phases. Now moon also goes through the phases as it goes around the earth. After all, both moon as well as Venus, they reflect by sunlight. So as the angle at which the sunlight falls on these planets varies with respect to the position of the earth in space, you will find that different fractions of that body is illuminated as seen from earth, and this is what we call phases. But the interesting thing is the crescent Venus is larger than the full Venus, whereas the crescent moon is not bigger than the full moon. So if you look at the size of the moon's disk, it is always the same no matter what the phase of the moon is. Okay, that is because the moon is going around the earth, and the distance between the earth and the moon doesn't vary much. Whereas in the case of Venus, the variation in distance will be so much that you would expect a big change in the size of crescent Venus and full Venus. And what did Galileo observe? This is Galileo's beautiful hand drawing. I mean, whenever I see this drawing, I feel really excited, mainly because of two things. One, the telescope that Galileo used to observe this and record this was a very, very primitive one. Primitive by today's standards. See, I have not seen through a telescope of that kind, but I have heard from people who have used a telescope which is of the same power as Galileo's telescope. They say that you hardly can actually make out the difference between the crescent Venus and full Venus. The resolution is not all that great. Though the magnification is good, the resolution is not very good. But Galileo was a keen observer. He observed not only through the telescope with his through his eye, he also observed through his mind's eye, like a keen artist does. You know, artists have a particular sense of perception and observational skills which normally people would not have. That is what differentiates a great artist from an ordinary man like me. Galileo made this beautiful drawing. ಈ ಡ್ರಾಯಿಂಗ್ ಅಲ್ಲಿ ನೋಡಿ, ಪೂರ್ಣ ಶುಕ್ರ ಗ್ರಹ ಮತ್ತೆ ಬಾಲ ಶುಕ್ರ ಗ್ರಹದ ಗಾತ್ರದಲ್ಲಿ ಎಷ್ಟು ವ್ಯತ್ಯಾಸ ಇದೆ ಅಂತ ಹೇಳಿ. There is a huge difference. And look at Galileo's exclamation at this. He says very proudly, and I showed that Venus changed in shape resembling the moon. Oh, Nicholas Copernicus, what a pleasure it would have been for you to see this part of your system confirmed by so clear an experiment. ಯಾಕೆಂದ್ರೆ ಇದು ಸೌರ ಕೇಂದ್ರವಾದ ಸರಿ ಇದೆ ಅಂತ ನಾವು ಒಪ್ಕೊಳ್ಳೋದಾದ್ರೆ, ಈ ಶುಕ್ರ ಗ್ರಹ ಸೂರ್ಯನ ಸುತ್ತ ಸುತ್ತಬೇಕು. ಸೂರ್ಯನ ಸುತ್ತ ಸುತ್ತುವ ಶುಕ್ರ ಗ್ರಹ ಈ ರೀತಿಯಾಗಿ ಗಾತ್ರದಲ್ಲಿ ವ್ಯತ್ಯಾಸ ಆಗ್ತಾ ಇರುತ್ತೆ. ಮತ್ತೆ ಅದು ಯಾವ ಆಕಾರದಲ್ಲಿ ಕಾಣುತ್ತೆ ಭೂಮಿಯಿಂದ, ಅದರಲ್ಲೂ ವ್ಯತ್ಯಾಸ ಆಗುತ್ತೆ. ಇವೆಲ್ಲವನ್ನು ಕೋಪರ್ನಿಕಸ್ ಮುಂಚೆನೆ ಹೇಳಿದ್ರು. And Galileo beautifully verified this through his telescopic observations. Now, I have to mention one thing. The angular size, the angular size of Venus actually varies from 9.7 arc seconds to 1.6 arc seconds. Arc second ಅನ್ನೋದು ಕೋನೀಯ ಗಾತ್ರ. ಅದು ಎಷ್ಟು ದೊಡ್ಡದು ಅನ್ನೋದನ್ನ ನಾವು ಖಗೋಳ ಕಾಯಗಳ ಬಗ್ಗೆ ಮಾತಾಡುವಾಗ ಈ ಒಂದು ಮಾನದಂಡವನ್ನು ಉಪಯೋಗಿಸ್ತೀವಿ in terms of arc seconds to determine to express the size of a celestial body. So 1 degree on your protractor is 3600 arc seconds. So this variation in the size of Venus is from 1.6 arc seconds to 9.7. 9.7 when it is nearest to us, 1.6 when it is farthest from us. Now in this diagram, I have deliberately tried to put a line here as a diameter for the full Venus, and I've used this as one unit, and I put this one below the other for the crescent Venus, and actually I get 6 units of this particular length. 6 units of this particular length. And you see that this angular size also varies by a factor of 6. 16 6 are 96, right? So what a great artist Galileo was. He not only documented what he saw through the telescope, he documented faithfully the angular size of Venus also. And it is this kind of skill for which we admire Galileo and his contributions. Okay, so on the right hand side, you have actually photograph of a full Venus to crescent Venus taken through the same camera with the same settings on different dates, of course. Dates are also mentioned there. So what you find is that the full Venus is much smaller than the crescent Venus. And actually, if you did this exercise of putting this full Venus on the crescent Venus, you'll find that 6 of them will actually fit in, and that goes to show how keen an observer the great Galileo was. So up to this point, so we see that we talked about solar system as an entity, and this entity has some center of revolution. In one model we had Earth, in another model we have the Sun, and then the sun-centered model made a very important prediction that phases of Venus would be seen, and the angular size of Venus would change, but the actual size of Venus will not change. Only the angular size as seen from Earth would be changing, and all these have been spectacularly verified. So which means our strength of belief in heliocentric model goes up by several notches. The planet Mars, ಈಗ ಮಂಗಳ ಗ್ರಹದ ಬಗ್ಗೆ ನಾವು ಮುಂಚೆನೂ ಮಾತಾಡಿದ್ವಿ, ಅದು ಹಿಮ್ಮುಖ ಚಲನೆ ಎಷ್ಟು ಕ್ಲಿಷ್ಟಕರವಾದಂಥ ಪ್ರಶ್ನೆಗಳನ್ನ ಮೂಡಿಸ್ತು ಅಂತ ಹೇಳಿ. ಅದೇ ರೀತಿ ಮತ್ತೊಮ್ಮೆ ಈ ಮಂಗಳ ಗ್ರಹದ ಬಗ್ಗೆ ನಾವು ಅಧ್ಯಯನ ನಡೆಸೋ ಒಂದು ಪ್ರಮೇಯದಲ್ಲಿ ಬಹಳ ಮುಖ್ಯವಾದಂತಹ ಅಂಶಗಳನ್ನ ಇಲ್ಲಿ ಕಂಡುಹಿಡಿಯೋದಕ್ಕೆ ಸಾಧ್ಯ ಆಯಿತು. ಸೊ ವಾಟ್ ಆರ್ ದ ಥಿಂಗ್ಸ್ ದಟ್ ವಿ ಹ್ಯಾವ್ ಡಿಸ್ಕವರ್ಡ್ ಬೈ ವರ್ಚ್ಯೂ ಆಫ್ ಸ್ಟಡಿಂಗ್ ಮಾರ್ಸ್? The problem of orbit of Mars, as it is popularly called, was a very formidable problem, a very difficult problem. And the problem was actually about the shape of the orbit of planet Mars. Adu ಮಂಗಳ ಗ್ರಹದ ಕಕ್ಷೆ ಏನಿದೆ ಅದು ವೃತ್ತಾಕಾರವಾಗಿ ಇಲ್ಲ ಅನ್ನೋದು ಭಾಸವಾಗ್ತಾ ಇತ್ತು. ಆದರೆ ವೃತ್ತಾಕಾರವಾಗಿಲ್ಲ ಅನ್ನೋದಾದ್ರೆ ಅದು ಯಾವ ಆಕಾರದಲ್ಲಿದೆ ಆ ಕಕ್ಷೆ ಅನ್ನೋದು ಒಂದು ದೊಡ್ಡ ಪ್ರಶ್ನೆ ಆಗಿತ್ತು. And this was an interesting question as to what the shape of the Mars's orbit is. In fact, the deviation of Mars's orbit from its circular path is very small. ಇಲ್ಲಿ ನಾನು ಹಾಕಿರೋ ಒಂದು ವೃತ್ತ ಇದೆಯಲ್ಲ, ಇಲ್ಲಿ ಕೆಂಪು ಬಣ್ಣದ ವೃತ್ತ, ಅಲ್ಲಿ ಎರಡು ಫೋಟೋಗಳನ್ನ ಅಂಟಿಸಿದ್ದೀನಿ. ಒಂದು ವೃತ್ತಾಕಾರವಾಗಿರುವಂತಹದ್ದು, ಇನ್ನೊಂದು ಮಂಗಳ ಗ್ರಹದ ಕಕ್ಷೆಯ ಆಕಾರ ಏನಿದ್ದು ಅದನ್ನ ಈ ವೃತ್ತದ ಮೇಲೆ ಅಂಟಿಸಿರೋದು. Now, if the deviation from the circle is a lot, then you would see the two images as a separate images, which I have superposed there, but you actually see only one curve there. And this is because the deviation of the orbit of Mars from being a circular orbit is so small that it is less than the thickness of the line that you see in this picture. So for all practical purposes, it can be treated as a circular orbit. But then for real things, you can't treat it as a circular orbit. And this was the question that bugged many astronomers for a very long time. And one of them was Tycho Brahe. So Tycho Brahe ಅನ್ನೋರಿಗೆ ಈ ಒಂದು ಪ್ರಶ್ನೆ ಮಂಗಳ ಗ್ರಹದ ಕಕ್ಷೆಯ ಆಕಾರದ ಬಗ್ಗೆ ತುಂಬಾ ಕುತೂಹಲ ಇತ್ತು. ಹಾಗಾಗಿ ಅವರು ದೊಡ್ಡ ಯಂತ್ರಗಳನ್ನ ರಚಿಸಿ ತುಂಬಾ ಸೂಕ್ಷ್ಮವಾದಂತ ಮಾಪನಗಳನ್ನ ಮಾಡಿದ್ರು. ಈ ಮಾಪನಗಳನ್ನ ಉಪಯೋಗಿಸಿಕೊಂಡು ಯೋಹಾನಸ್ ಕೆಪ್ಲರ್ ಅನ್ನೋರು ಈ ಪ್ರಶ್ನೆಗೆ ಉತ್ತರವನ್ನ ಕಂಡು ಹಿಡಿಯೋದ್ರಲ್ಲಿ ಸಫಲರಾದರು ಅಂತ ಹೇಳ್ಬೋದು. So Tycho Brahe collected data painstaking data actually over a period of 20 long years. There you see Tycho Brahe in his observatory using gigantic instruments, huge protractors actually, and using them, he made extremely precise measurement of positions of planets and other celestial objects whenever the night skies were clear over a period of 20 long years. And that data was given to Kepler when Tycho Brahe died, and Kepler used that to find out the actual shape of the orbit of Mars. When Kepler looked at the data, ಅದು ಎಷ್ಟೊಂದು ದತ್ತಾಂಶ ಇತ್ತು ಅಂತ ಹೇಳಿದ್ರೆ ಕೆಪ್ಲರ್ ಏನ್ ಹೇಳಿದ್ರು ಅಂದ್ರೆ ಈ ಮಂಗಳ ಗ್ರಹದ ಕಕ್ಷೆಯ ಆಕಾರದ ಪ್ರಶ್ನೆ ಏನಿದೆ ಇದನ್ನ ನಾನು 8 ದಿವಸಗಳಲ್ಲಿ ಕಂಡು ಹಿಡಿಯೋದಕ್ಕೆ ಸಾಧ್ಯ ಆಗತ್ತೆ ಅಂತ ಹೇಳಿ ಅವರು ಒಂದು ಘೋಷಣೆ ಮಾಡಿದ್ರು. ಆದರೆ ಆ ಪ್ರಶ್ನೆಗೆ ಉತ್ತರವನ್ನ ಕಂಡು ಹಿಡಿಯೋ ಅಷ್ಟರಲ್ಲಿ ಅವರಿಗೆ 8 ವರ್ಷಗಳೇ ಬೇಕಾಯ್ತು. He took 8 long years and not 8 days as he claimed to find the solution to the problem of Mars's orbit. And when he had done it, he wrote, Mars alone enables us to penetrate the secrets of astronomy, which otherwise would remain hidden from us. ಅಂದ್ರೆ ಈ ಮಂಗಳ ಗ್ರಹದ ಕಕ್ಷೆಯ ಪ್ರಶ್ನೆಗೆ ಉತ್ತರವನ್ನು ಕಂಡುಹಿಡಿಯುವ ಒಂದು ಮಾರ್ಗದಲ್ಲಿ ಕಂಡುಹಿಡಿಯುವ ನೆಪದಲ್ಲಿ ನಾವು ಖಗೋಳ ವಿಜ್ಞಾನವನ್ನೇ ಬೇರೆ ದಿಕ್ಕಿನಲ್ಲಿ ಸಾಗೋ ಹಾಗೆ ಮಾಡುವಂತ ಶಕ್ತಿ ಆ ಪ್ರಾಬ್ಲಮ್ಗಿತ್ತು, ಆ ಒಂದು ಪ್ರಶ್ನೆಗಿತ್ತು ಅಂತ ಇವರು ಕೆಪ್ಲರ್ ಹೇಳ್ತಾರೆ. ಅಂಡ್ ಅದು ಅತಿಶಯೋಕ್ತಿನೂ ಅಲ್ಲ, ಆಸ್ ವಿ ವಿಲ್ ಸಿ very shortly. It is not an exaggeration when Kepler makes this particular statement. So he found out that this is not circular, and if it is not circular, what exactly is it? And in his time, and also in times before Kepler, this was a very famous problem, and a lot of people actually spent a lot of time in trying to understand this problem, and they got frustrated and they gave up the problem, and some of them are supposed to have turned hysterical at the inability to solve this problem. So this is a cartoon by our friend Mr. B.G. Gujarappa, who made for one of the planetarium shows. This is Joachim Rheticus. He was an assistant of Copernicus, and when he could not solve the problem by normal mathematical means, he took to conjuring up spirits, and there he is asking a genie to appear before him so that the spirit would be able to solve this particular problem of orbit of Mars. And the spirit duly appears there, and this man states the problem to the genie, and what the spirit does is that it holds Rheticus by the scruff of his collar and bangs his head on the ceiling, and then flings him to the floor and walks away, saying that this is the orbit of planet Mars. This is just to tell you, the story is repeated in many authentic by many authentic sources. The spirit might not have really come there and flung him on the floor, but it shows the extent of exasperation that astronomers had to solve this problem. Now, Kepler was not the kind of person who really gave up these things very easily. He found out that in order to solve the problem of Mars's orbit, it was important to know where the Earth's position was when Tycho Brahe made this measurement of positions of planet Mars. Therefore, in order to know the position of Earth in space at all times when Tycho Brahe measured the position of planet Mars, he used an ingenious method. It requires nothing more than 7th standard geometry, but a lot of imagination. So I leave it to you as some kind of an assignment if you would like to do. But the important thing is that he solved that problem, and he found, to his surprise, that Earth actually moved around the sun. Therefore, the Copernican model tells you that sun at the center is a nice way to represent the arrangement of planets in the solar system. but Kepler's work actually showed that there is no way other than planet Earth going around the sun. So he established it unambiguously in the process of solving this particular problem. And that is a very, very big achievement in astronomy in his time, because not many people were ready to believe that Earth moves and Earth moves around the sun. And in the process of finding out the position of Earth in space, when Tycho Brahe made those measurements, he found out that Earth did not move at a constant speed around the sun. It moves at different speeds at the different times of the year. And surprisingly, he found that the line joining the sun and the planet Earth, it swept equal areas in equal intervals of time. So in different months, the area swept were exactly the same if you kept the same number of days. So this became the first law of planetary motion, and that had a very big impact, as we shall see later on. And then we will cut the long story short, because how he arrived at the fact that the shape of the orbit of Mars is ellipse is another very interesting story. He actually knows that it is not circular orbit, and if it is not circular, what else is it? And then he himself finds out that it is an oval. It is an oval. The drawing on the screen that you find on the right hand side is highly, highly exaggerated. The orbit of Mars is not so much deviant from a circle. It's very, very small, as I told you earlier, but it's some kind of an oval. Now, oval is actually not the shape of, it's not one particular shape. It actually is a family of curves in geometry. So you have to tell what exactly is what type of oval it is. And Kepler found out that it is the familiar ellipse, after he had tried out 70 different kinds of shapes, and then he made almost 1,000 pages of calculations. He found out that solution to this problem, that the shape of Mars's orbit is an ellipse. Of course, if you take any difficult problem and then you spend 1,000 pages to solve it, that will not help you to arrive at the solution. You have to be a Kepler in order to do that. So Kepler showed that the orbit of Mars was an ellipse, and since he plotted the position of Earth at all times when the position of Mars had been measured by Tycho, he found out that the Earth's orbit is also an ellipse. So both Earth and Mars had elliptical orbits, and there is no reason for him to disbelieve that other planets were of a different orbital shape. So he generalized that all planets moved in elliptical orbits. ಇಲ್ಲಿ ಒಂದು ತುಂಬಾ ಗಮನಾರ್ಹವಾದಂತ ಅಂಶ ಅಂತ ಹೇಳಿದ್ರೆ, ಕೊಪರ್ನಿಕಸ್ ಹೇಳಿದಂತ ಒಂದು ಮಾದರಿಯಲ್ಲಿ ಗ್ರಹಗಳೆಲ್ಲ ವೃತ್ತಾಕಾರದಲ್ಲಿ ಚಲಿಸ್ತಾ ಇದ್ವು ಮತ್ತೆ ಒಂದೇ ಗತಿಯಲ್ಲಿ ಚಲಿಸ್ತಾ ಇದ್ವು. It was circular and it was uniform. But what Kepler had determined was something which was not inferior to any kind of a revolution that you can think of, revolution in the mind. He showed that the orbit is not circular and that the speeds are not uniform. So two very important tenets on which Ptolemy and Copernicus came up with their models of the universe were thrown away by sheer logic and mathematical calculations of Kepler. So it was not circular, it was not uniform, really shattering. And after 9 years of work further, he determined the third law of Kepler's planetary motion, what we call the law of periods. So he found out a relationship between the time taken by a planet to go around the sun once and the distance of the planet from the sun. Now in the process, again, this is not a very easy problem. I can tell you, graph ಅಲ್ಲಿ plot ಮಾಡಿದ್ರೆ ಒಂದು ಕಡೆಗೆ ಗ್ರಹಗಳ ದೂರ ಮತ್ತೆ ಇನ್ನೊಂದು ಕಡೆಗೆ ಗ್ರಹಗಳು ತೆಗೆದುಕೊಳ್ಳುವಂತಹ ಅವಧಿ ಸೂರ್ಯನ ಸುತ್ತ ಸುತ್ತೋದಕ್ಕೆ ಆ ಗ್ರಾಫ್ ಅಲ್ಲಿ ಏನಾಗುತ್ತೆ ಅಂತ ಹೇಳಿದ್ರೆ ಈ ತರದ ಒಂದು ಕರ್ವ್ ಬಂದ್ಬಿಡುತ್ತೆ. ಈ ತರ ಕರ್ವ್ ಬಂದಾಗ ಈ ದೂರಕ್ಕೂ ಮತ್ತೆ ಅವಧಿ ಏನ್ ತೆಗೆದುಕೊಳ್ಳುತ್ತೆ ಅದು ಸೂರ್ಯನ ಸುತ್ತ ಹೋಗೋದಕ್ಕೆ ಒಮ್ಮೆ ಇವುಗಳ ನಡುವೆ ಇರುವಂತಹ ಒಂದು ಸಂಬಂಧವನ್ನ ನಾವು ಕಲ್ಪಿಸೋದಿಕ್ಕೆ ತುಂಬಾ ಕಷ್ಟ ಆಗುತ್ತೆ. ಇಟ್ ಇಸ್ ಇಂಪಾಸಿಬಲ್ ಇನ್ ಫ್ಯಾಕ್ಟ್. ಸೊ ಯು ಆಲ್ವೇಸ್ ಪ್ಲಾಟ್ things on x and y axis in such a way that the curve is always a straight line, and when you get that straight line, then what you have plotted on x axis is directly proportional to what you have plotted on the y axis. So it turned out that it was t square proportional to a cubed, and in order to do this, Kepler had to invent logarithms and properties of logarithms and use them to make these kind of plots. Linear plots will be very, very difficult, and I think it is almost impossible for anybody to come up with t square proportional to a cube. So logarithmic plot is very important, and Kepler invented even that for his own sake. It had been invented before him by John Napier 7 years before him, but it was not in a form that he could apply to solve this particular problem, and so he modified it. That goes to Kepler's credit again. Again, the inspiration is a solar system object and a problem that comes with it. I think I'm running out of time, therefore I will slightly fast forward in the next 10 minutes or so, just to give you a glimpse of how solar system has been responsible for coming up with the various ideas that have been tested, verified, and sometimes beyond that. So Kepler na samakalina antane helbodu navu Galileo Galilei. So we saw Galileo Galilei earlier in the context of Venus, planet Venus, and here he is again, and he makes some wonderful and revolutionary telescopic observations. And in this particular painting that you see, what I like is that the artist has depicted Galileo as not only as a scientist but also as an artist. So he's there making some very meticulous details. He's documenting meticulous details that his eye is watching through the telescope. Okay, so what did he find out? He found out that the moon is not a smooth object as we believe. When I say we believe, it was in his time. The philosophy demanded that all the celestial objects be plain and smooth and so on. But what he found out was that the moon's surface was very rough. It was very much like Earth, mountains, valleys, and then craters, and maybe even potholes like you find on Bangalore roads. All these features were there on moon, which made Galileo to say that moon is not very different from the Earth. And that was a very big blow to the philosophies of his time. And just to show you what a great artist that Galileo was, on the right hand side is the drawing of the moon and its features by Galileo. On the left hand side is a photograph of the same region. Look at the details that he has been able to get. ಎಡಗಡೆ ನೀವು ಏನು ಫೋಟೋಗ್ರಾಫ್ ಅಲ್ಲಿ ನೋಡ್ತೀರಾ, ಆ ಪ್ರತಿಯೊಂದು ಅಂಶವು ಇಲ್ಲಿ ಬಲಗಡೆ ಗ್ಯಾಲಿಲಿಯೋ ಮೂಡಿಸಿರುವಂತಹ ಒಂದು ಚಿತ್ರದಲ್ಲಿ ಕಾಣಬಹುದು. ಅದು it may be the features, size of the features, position of the features, all of them are so meticulously replicated by Galileo. Okay, so that goes to show what a fantastic observer Galileo was. And Galileo considers this particular observation as the most important of all his observations, and that is the observation of planet Jupiter. Now, this Galileo was a very, very clever scientist. He was very articulate. He was very clever. He knew what he was actually trying to do. You see, there is one way of doing science. You know, you keep on working on one research problem after another. ಬೇರೆ ಬೇರೆ ಆದಂತಹ ಪ್ರಾಬ್ಲಮ್ಗಳನ್ನ ನೀವು ರಿಸರ್ಚ್ ಮೂಲಕ ಸಂಶೋಧನೆ ಮೂಲಕ ನೀವು ಈ ಉತ್ತರಗಳನ್ನ ನೀವು ಕಂಡುಹಿಡ್ಕೊಳ್ತಾ ಹೋಗ್ಬೋದು. ಇನ್ನೊಂದು ಏನಪ್ಪಾ ಅಂತ ಹೇಳಿದ್ರೆ, ನೀವು ಒಂದು 10 ವರ್ಷ 20 ವರ್ಷ ನೀವು ಸಂಶೋಧನೆ ನಡೆಸಿದ ನಂತರ ಈ 10 ಅಥವಾ 20 ವರ್ಷಗಳ ಸಂಶೋಧನೆಗಳನ್ನೆಲ್ಲ ನಾವು ಕ್ರೋಢೀಕರಿಸಿ ನೋಡಿದಾಗ ನೀವು ಯಾವುದೋ ಒಂದು ಮಹತ್ತರ ಸಂಶೋಧನೆ ಮಾಡಿದ್ದೀರಾ ಅಂತ ಅನ್ನಿಸ್ಬೇಕು. This is one of the ways in which great researchers work for their lifetime. So there would be a lot of small problems that you solve, or very interesting problems that you solve. And when you put all these interesting problems together, there would be a solution to a great problem that is bothering you. And that's exactly what we see in Galileo's work. Galileo was a Copernican. He believed in heliocentric theory, even though many people in his time did not. Therefore, he used every observation that he made through his telescope to serve as an evidence for heliocentrism. So, ಪ್ರತಿಯೊಂದು ವೀಕ್ಷಣೆನು ಈ ಸೌರಕೇಂದ್ರವಾದಕ್ಕೆ ಒಂದು ಪುರಾವೆ ಅನ್ನೋ ರೀತಿಯಲ್ಲಿ ಅಥವಾ ಪುಷ್ಟೀಕರಣ ನೀಡುತ್ತೆ ಅನ್ನೋ ರೀತಿಯಲ್ಲಿ ಗೆಲಿಲಿಯೋ ತಮ್ಮ ದೂರದರ್ಶಕಗಳ ಮೂಲಕ ವೀಕ್ಷಣೆಗಳನ್ನ ನಡೆಸ್ತಾ ಇದ್ರು. Now what you see here is actual notebook writings of Galileo. See, it's so crude. There is a circle, which is a big circle that represents Jupiter, and then there are some star-like things, asterisks on either side of Jupiter or one side of Jupiter. In fact, he called these objects stars when he saw through the telescope. They seem to be very close to Jupiter and almost along the equator of Jupiter. And he found out through his observations over several weeks that these stars are actually going around planet Jupiter. Now, that's a very, very important discovery that he makes, because he showed that there is nothing special about Earth being the center. Remember, even in Galileo's time, the debate between heliocentric model and geocentric model was still going on. It was a raging debate. ಭೂಕೇಂದ್ರವಾದ ಮತ್ತೆ ಸೌರಕೇಂದ್ರವಾದದ ಬಗ್ಗೆ ಸಾಕಷ್ಟು ಚರ್ಚೆ ನಡೀತಾ ಇತ್ತು ಗೆಲಿಲಿಯೋ ಇದ್ದ ಸಂದರ್ಭದಲ್ಲಿ. ಇಲ್ಲಿ ಗೆಲಿಲಿಯೋ ತೋರಿಸಿಕೊಟ್ಟಿದ್ದೇನು ಅಂತ ಹೇಳಿದ್ರೆ, ಭೂಮಿ ಒಂದೇ ಕೇಂದ್ರವಾಗಿರೋದಕ್ಕೆ ಏನೋ ಒಂದು ದೊಡ್ಡ ಕಾರಣ ಇರೋದಕ್ಕೆ ಸಾಧ್ಯ ಇಲ್ಲ. ಯಾಕೆ ಅಂತ ಹೇಳಿದ್ರೆ, ಇಲ್ಲಿ ಗುರುಗ್ರಹ ಏನಿದೆ ಅದರ ಸುತ್ತ ಕೂಡ ಸುತ್ತುವ ಕಾಯಗಳನ್ನ ನಾವು ನೋಡಬಹುದು. ಇದರ ಮೂಲಕ ನಾವು ಏನು ಪುಷ್ಟೀಕರಣ ನೀಡಬಹುದು ಅಂತ ಹೇಳಿದ್ರೆ, ಭೂಮಿಯ ಹಾಗೆಯೇ ಇನ್ನೊಂದು ಕೇಂದ್ರವೂ ಇರೋದಕ್ಕೆ ಸಾಧ್ಯ ಅಂತ. There can be another center of revolution in the solar system. And in those days, solar system was the universe. Therefore, Earth need not be the center of revolution in the universe. There could be another center of revolution. So nothing special about Earth. So indirectly, he's saying that the sun can be the center of revolution. So he's a very clever man. But for all that things that Galileo did, he was told that the telescope that through which he was seeing was actually some kind of a devil's toy, which manifested objects which really did not exist in nature. And they said that it was some artificial thing that was created by the telescope. So ಆಕಾಶದಲ್ಲಿ ಇಲ್ಲದೆ ಇರುವಂತಹ ವಸ್ತುಗಳನ್ನು ಕೂಡ ಈ ದೂರದರ್ಶಕ ಅನ್ನೋ ಒಂದು ಪೆಟ್ಟಿಗೆ ಏನಿದೆ ಅದು ಕೃತಕವಾಗಿ ನಿರ್ಮಿಸ್ತಾ ಇದೆ ಅಂತ ಹೇಳಿ ಬಹಳಷ್ಟು ಜನ ಏನೆಲ್ಲ ಪುರಾವೆಗಳನ್ನ ಗೆಲಿಲಿಯೋ ಮುಂದೆ ಒಡ್ಡಿದ್ರು ಅದನ್ನೆಲ್ಲ ತಳ್ಳಿ ಹಾಕೋದಕ್ಕೆ ಈ ಒಂದು ರೀತಿಯ ಯೋಚನೆಯನ್ನು ಹಲವಾರು ಜನ ಮಾಡಿದ್ರು. So these are the 4 Galilean satellites as seen through the present day telescopes or through Voyager missions. And you find that Galileo is very proud that the observations that he made about these are the most important ones, because he knows that through this he can establish that Earth is not the only center of revolution. Okay. Then he also showed that sun has spots, therefore sun is not blemishless. So sun is not pure, it has spots. So all these things were very important in Galileo's mind to show that heliocentric idea is correct. It's another story that many people did not take his ideas as scientific evidence. So maybe I will, Professor Ajit, how many more minutes am I allowed to take?
How about another 5 minutes or so?
Another 5 minutes? So yeah. I'll have to go at the speed of light.
We could do it 10 then.
Okay. I will not exceed 10. I will take 10 minutes. there are 3 or 4 very important and big ideas which I'm coming to, and I would like to at least place those before I end my time. So nature of speed of light is another very important question. What kind of what is actually light, and at what speed does it move? So for a long time, people thought that light could be a particle, light could be a wave, and then light could actually move at an infinite speed. So which means light could go from one point to another point in 0 seconds. And it was perfectly all right for people to think like that for a very long time. But again, it is our great Galileo who does an experiment like this animation shows on the screen. I hope the animation is played out. So what Galileo does is to directly measure the time taken by light to go from his lantern to his friend's lantern and come back. He knows the time taken between these two, between this whole circuit, for one whole circuit of light going and coming back. Therefore, the speed of light is distance traveled by time taken. In fact, Galileo was the one who defined the speed this way. Before that, speed had not been defined scientifically at all. So Galileo defines the speed, and he uses that definition to exactly measure the speed of light. And he finds the speed of light to be 10 times the speed of sound. Now, modern day students will say that this is an experiment with a huge error, several magnitudes, orders of magnitude, because we know that it's the speed of light is something like 1,000 times the speed of 100 times the speed of sound. But then this says only 10 times. But forget about the accuracy of the measurement. But what is important is the fact that you want to do an experiment to check if speed of light is infinite or finite. Galileo established that it is finite, and 10 times the speed of sound in Galileo's time is a huge speed. Actually, there was no object that actually traveled at 10 times the speed of sound. Most objects around us don't travel at 10 times the speed of sound. Therefore, that was a speed big enough to describe light. But then the actual order of magnitude of speed of light was established by Ole Romer when he was actually trying to solve a problem related to longitude. So he wanted to fix the longitude of different places on the Earth, and he was in the Paris observatories working on this particular problem. And as luck would have it, he was studying the eclipse of one of the satellites of Jupiter that Galileo had discovered. It's called satellite Io. And when you look at the eclipse time of Io, when Earth is at different positions around the sun, that is at different times of the year, what Romer found was that there was a systematic variation in the predicted time of eclipse of Io and the observed time of the eclipse of Io from the Earth. Okay, and the calculation itself could be done on the basis of Kepler's laws of planetary motion. They apply well even to the satellites of Jupiter, not merely for planets going around the sun. So he found that there was a systematic variation, and he showed through his calculations that this variation was actually because when the Earth was at different positions around the sun, the light reaching us from Io would take different times, because it has to travel an extra distance or it has to travel a shorter distance. Now, through this, he actually found out the speed of light by looking at the discrepancy between the observed time of the eclipse and the calculated time of eclipse. He found out that light takes a finite time to reach us, and he got something like 2 lakh and a little more than that kilometers per second. Now that's a huge number compared to 10 times the speed of sound. Now, if you have to do an experiment on the Earth to find the speed of sound, to find the speed of light, then you know what kind of precision is required, and you know how big the number is that you are going to measure. So you have some background information to plan an experiment in a laboratory here. But for Romer, the laboratory, the grand laboratory, was the satellite of Jupiter going around Jupiter. So that enabled us to estimate the speed of light, and that has very big, that made very big changes in physics, and not only on the speed of light, but even on many other questions. Okay, so that's the speed of light. And of course, we cannot end without a reference to Newton's inspiration drawn from the moon. And the legend is that he saw an apple falling and he was inspired by a falling apple. Inspired, yes, he was, but not by the apple falling on his head, as stories would tell you. What he wondered was, whatever the force that is responsible for the apple to fall on the earth here, can that force in principle be extended all the way to the moon? And would that force be big enough to hold the moon in its orbit? And while contemplating on this problem, he took 20 long years to solve this problem. In fact, great problems take a great length of time because of the tools that are required to solve the problem would not be there already. So in the case of Newton, all the mathematical tools were not in place, and he had to master them and then put them to use. And he showed that indeed the force that causes the apple to fall on the earth is also responsible for the moon going around the earth. And he formulated the law of gravitation from this, the inverse square law. And this is the first law in physics which could be equally applicable on Earth as well as on outside the Earth. So truly it was a universal law, the first of its kind. And using that, Newton was able to solve almost all the astronomical problems of his time. And that is the key to the success of law of gravitation. So Gurutva Niyama ಏನು ಕಂಡುಹಿಡಿದ್ರು ಅದು ಚಂದ್ರನ ಚಲನೆಯ ಅಧ್ಯಯನದ ಮೂಲಕ ಮಾಡೋದಕ್ಕೆ ಸಾಧ್ಯ ಆಯಿತು. ಇದರಿಂದಾಗಿ ಆಗಿನ ಕಾಲದಲ್ಲಿ, ನ್ಯೂಟನ್ ಇದ್ದಂಥ ಕಾಲದಲ್ಲಿ, ಖಗೋಳಶಾಸ್ತ್ರಕ್ಕೆ ಸಂಬಂಧಪಟ್ಟ ಎಲ್ಲ ಪ್ರಶ್ನೆಗಳನ್ನು ಉತ್ತರಿಸೋದಕ್ಕೆ ಸಾಧ್ಯ ಆಯಿತು. And the important thing is this: you have to change your attitude when everybody sees that the moon is going around the earth in a circular orbit. Newton felt that the moon is actually falling towards the earth. Now, Newton was fresh from his laws of mechanics, laws of motion. So inertia would take moon in a straight line as shown by this arrow. So after a particular amount of time, the moon, which is here now, would be at the end of the arrow tip here. But actually the moon is here in its orbit, circular orbit. So while everybody sees the earth going, moon going around the earth, Newton actually sees that the moon has actually fallen by a certain height from where it should have been. So one has to be a Newton to see this kind of a perspective. And I think I will end with this particular interesting note. That is the discovery of planet Neptune. Like I told you earlier, a great theory predicts. And sometimes a great theory, while it tries to explain, or it explains all the phenomena known at that time, like I told you, Newton was successful in answering all of them. Sometimes there may be something else that you would discover later on, and a great theory would absorb even that something else. Now, Kepler's laws of planetary motion, it was formulated with the data that we had about 6 planets known at that time, up to Saturn. But later, when Uranus and Neptune were discovered, the laws of planetary motion were not disturbed. these two planets also were behaving exactly as given by the Kepler's laws of planetary motion. Now, in the same way, when people observed planet Uranus, it was the first planet to be discovered that was not visible to the naked eye. ದೂರದರ್ಶಕದ ಮೂಲಕ ಯುರೇನಸ್ ಗ್ರಹವನ್ನ ಪತ್ತೆ ಆವಿಷ್ಕಾರ ಮಾಡಿದ್ರು. ಆವಿಷ್ಕಾರ ಇದು ಅದರ ಮುಖಾಂತರ ನೋಡಿದ ಒಂದು 30-35 ವರ್ಷಗಳಲ್ಲಿ ಈ ಯುರೇನಸ್ ಗ್ರಹದ ಕಕ್ಷೆಯಲ್ಲಿ ಒಂದಷ್ಟು ಬದಲಾವಣೆಗಳನ್ನು ನೋಡಿದ್ರು. There were some perturbations in the orbit of Uranus. So people started wondering if Newton's law of gravitation did not work at that distance, or if Newton's law of gravitation had to be modified and so on. And at that time, these two gentlemen, Joseph Leverrier and J.C. Adams, they used the same law which was being doubted by others, namely the Newton's law of gravitation, and showed that Uranus would be slightly disturbed in its orbit, provided there is a massive object close by. So they estimated the mass of that object. They could also pinpoint in which part of the sky you could find it. And when people turned their telescopes to that part of the sky, lo and behold, a new object, Neptune, was sitting there. Therefore, whatever the law that was being doubted was used efficiently by Leverrier and J.C. Adams. Of course, it was not a very easy problem to solve. In the process, they had to develop some new mathematical tools, but they did that, and they showed that there was nothing wrong with the Newton's law of gravitation, at least in the solar system. So that was a crowning glory moment for Newton's law of gravitation. But then, as it happens very often in science, just when you think that you are very comfortable and you have understood your solar system, in this example, in today's presentation, you have understood everything and you know how planets move and why Kepler's laws of planetary motion works and so on, then nature has a way to spring a surprise, and the surprise came in the form of a very small misbehavior from planet Mercury as it went around the sun. And Newton's law of gravitation was insufficient actually to completely account for this misbehavior of Mercury's motion around the sun, and that triggered another revolution in physics, another revolution in the theory of gravitation, which we call general theory of relativity. And general theory of relativity not only completely accounted for the motion of Mercury planet, it also went on to, like all great theories, predict phenomena that had not been observed by us. And in recent years, we have come to verify many of these things. And especially one of them is the gravitational lensing, the 100 years of which was recently celebrated. And Professor Ajit himself has given a wonderful talk, which you can find on ICTS channel on 100 years of gravitational microlensing. And again, that verification was possible only through by studying behavior of light in the solar system to start with, and then extended later outside the solar system. So to conclude, I would like to tell you that the solar system objects individually have been catalysts in the growth of physical theories. ಬಹಳಷ್ಟು ಯೋಚನಾವಳಿಗಳನ್ನ ಪ್ರೇರೇಪಿಸಿ ಮತ್ತೆ ಅವುಗಳಿಗೆ ಪುಷ್ಟಿ ಕೊಟ್ಟು ಮತ್ತೆ ಪೋಷಿಸಿ ಮತ್ತೆ ಅಲ್ಲಿ ಬಂದಂತಹ ಕ್ಲಿಷ್ಟಕರವಾದ ಪ್ರಶ್ನೆಗಳಿಗೆ ಉತ್ತರಗಳನ್ನ ಕಂಡುಹಿಡಿಯೋದ್ರಲ್ಲಿ ನಮ್ಮ ಸೌರವ್ಯೂಹದ ಕಾಯಗಳ ಪಾತ್ರ ಏನಿದೆ ಅದು ಬಹಳ ಮುಖ್ಯವಾಗಿದೆ. ಮತ್ತೆ ಸೌರವ್ಯೂಹವನ್ನ ನಾವು ಒಂದು ಎಂಟಿಟಿ ತರ ನಾವು ಟ್ರೀಟ್ ಮಾಡಿದ್ರೆ again it has given birth to lot of physical ideas which have been verified in the realm of solar system. And finally, I told you that solar system is a metaphor. So solar system ಅನ್ನೋದು ಒಂದು ನಾವು ಹೋಲಿಕೆಗೋಸ್ಕರ ಇಟ್ಕೊಳ್ಬಹುದು. So any object that you see out would also be behaving in some aspects like solar system object. So your physical theories can be extended beyond solar system, and it has been a very fruitful exercise for astronomers in the last few decades to see how Kepler's laws of planetary motions have also been very, very helpful in studying objects, studying phenomena beyond solar system, and it has been they have been rewarded with very, very important results, and physical theories have been once again verified by that. So at this point, I'll stop, and if there are some questions that I can answer, I will take. And once again, I would like to thank Professor Ajit and the ICTS team for this opportunity. So now, Professor Ajit.
Thank you very much, Mr. Madhusudan, for this very nice and very interesting perspective on the history of science. So there are lots of very nice, interesting questions on the chat box. So let me read out a few of them, if you could answer them. So one is, why are the orbits of the planets almost circular and not very eccentric ellipses?
Now, that has a very that could be answered at two different levels. So one, circle becomes a very special case of ellipse. Ellipse is the more general form that one can go with. And again, as Isaac Newton showed, when you have a gravitation, when you have these planets moving around the sun under force of gravity, and this force is an inverse square, this follows an inverse square law, 1 by r squared. That is, the force diminishes as the square of the distance. Under this kind of a force, there could be only some trajectories which are allowed. Circle and ellipses are also two of those. But then when you have a gravitational system, I mean, you are an expert on this, and if I'm imprecise, you can add to this. If you have two objects in a gravitational system going around one another, they might start to begin with as an elliptical orbit. And this elliptical orbit becomes more and more, it will move towards being more and more circular. Or in other words, its eccentricity will tend to be zero as it goes from ellipse to a circle. And this happens in all systems which are gravitationally bound over a very long time. So depending on at what period, after how much, after what time scale you observe a particular system, it would be perfectly circular or nearly circular or highly eccentric ellipse. So ultimately, all these elliptical orbits would go down to circular orbits in gravitationally bound systems.
Thank you. There is a clarification question. What is an epicycle?
What is?
An epicycle.
So this epicycle is that, let me see, is a small circle that moves on the larger circle in the Ptolemaic model. I'll just come to that particular slide very quickly. And yeah, I'm almost there. Yeah. So this small circle whose center moves on the larger circle is called the epicycle. This is the epicycle. And the size of the epicycle is decided by how many loops you want to make by the time that particular planet completes one revolution against the background of stars. Suppose you don't know whether this planet is going around the Earth or going around the Sun. It is still a debated question, let us say. But you can start with this particular planet in the neighborhood of a particular star, and then you wait after how many years on the Earth the planet actually comes back to the same position in the neighborhood of the same star. Now, in the process, how many times this loopy motion has been observed can be recorded, the retrograde motion, and accordingly, to account for the number of times the retrograde motion is observed in one revolution of the planet, the size of the epicycle is fixed accordingly.
Thank you. The next question is there any specific reason for all planets to rotate in the same direction? For example, counterclockwise.
Yeah, there is a reason. Now, if you take our solar system, our solar system was born out of a solar nebula. It was a huge collection of gas and dust initially, and the size of the solar nebula was several times the size of the solar system that we know today. And then it started collapsing under its own gravity, triggered by certain conditions, like a shock wave passing through this cloud of gas. Now that trigger would have some direction imparted to the motion of these gas particles. And as they keep collapsing, the direction of rotation is conserved by the conservation of momentum. If you now have to change the direction of momentum, you need a large torque acting on this gas dust. It happens in certain cases. For example, if you look at the planet Venus, it rotates in a direction that is opposite to the direction of rotation of other planets. Now, if you look at the conservation of angular momentum, it looks like Venus has violated that, but not quite. The theory is that at the time of the formation of this planet Venus, it must have collided with another Mars-sized planet at a glancing angle, and that would have actually made it go clockwise while all other planets are rotating anti-clockwise. So basically, the direction of rotation comes from the original direction of rotation of the solar nebula out of which these planets were created. If you have some other solar system outside our solar system, and people have seen many of them, so that may not be the same direction as our solar system's direction. So that would be a random choice.
Thank you. The next is an historical question. So what led Copernicus to produce the model that he did? What observations or ideas?
Copernicus, see, in Copernicus's time, most of these models were actually geometrical models. In fact, in the book De Revolutionibus that he wrote, in which all his model is completely explained, he says that this is a mathematical model. He doesn't make a statement that this is what he thinks the real system is actually. He says it's a mathematical model. So for him, replacing all these epicycles with the circles was more of a philosophical necessity and a geometrical simplicity, that circles are much easier to handle than all these large number of epicycles. I think in Ptolemy's model, there are something like 70 or 80 epicycles, and Copernicus reduced it to about 30 epicycles. And these epicycles were basically to account for the elliptical orbit of the planets and not for the retrograde motion. So it was much simpler. So what is pleasing to the eye and what is pleasing to the mind, that was the main motivation, that nothing can be more symmetric, more beautiful than circle. Nothing can be more easy to comprehend than uniform motion at a constant speed. So it is these kind of philosophies of the mind which goes into making the model. But sometimes your philosophy also works the nature also works exactly like your philosophical thinking, but sometimes it can be different.
Yeah. There is also a related question. How did Copernicus come up with values of distances of planets so accurately?
He actually does it in two different ways. One for planets which are between Earth and Sun, that is Mercury and Venus, and other one for planets which are beyond the Earth in terms of distance from the Sun. So what he does is, in fact, I just made a small calculation. What he does is, he looks at the number of years of observation. Let us say for Mars, you have about 79 years of observation. And in that process, in that period, Mars has actually completed 42 cycles around a star. Like I told you, you can have one reference star next to which you find Mars today. And then you find out when exactly Mars comes back to that particular point next to the star. And in the process, you know how many days have elapsed on the Earth. Okay. So For 79 years of observation, there are 42 cycles of Mars. For 71 years of Jupiter, there were, for 71 observations of Jupiter, there were 6 cycles that were observed. And for Saturn, over a period of 59 years of observation, there are only 2 times that planet Saturn came very close to that particular reference star. Okay. So now what he did was to find the ratio of these two numbers. How many years of observation divided by how many cycles of how many cycles that particular planet has gone through with respect to that star. That ratio gives the period of revolution of the planet around the sun. So you'll find, surprisingly, that for Mars, Copernicus came up with 687 days, and the modern value is also 687 days. Similarly, for Jupiter, 11.8 years by Copernicus and 11.86 by is the modern value. So like this, you find this is how Copernicus came up with the distance measurement for period of revolution for these planets.
Thank you. A lot of people have expressed their appreciation of the slides and the talk and so on. And there are many other interesting questions also. But because of the limitation of time, let me pick the last question, which is in Kannada. So maybe, I don't know if you can read it. I cannot read Kannada, unfortunately, yet. So this is from Akash Simha. Are you able to read that?
How do I go to that chat?
The chat, click your chat box. On Zoom, there is a chat link. Vijay, can you read it, please? Or Jiva, please? We will have to unmute you.
I'm unable to get that chat.
Yeah, that's okay. Vijay is going to read it.
Oh, Vijay is there?
Yes, I'm going to unmute Vijay.
That's just appreciation. ಎರಡು ಭಾಷೆಗಳಲ್ಲಿ ಹೀಗೆ ವಿಜ್ಞಾನದ ಭಾಷಣ ಕೊಡುವ ಸಾಮರ್ಥ್ಯ ಬಹಳ ಅಪರೂಪ.
Yes.
Thank you.
Okay, so maybe this is a good time to stop. We all appreciate this wonderful talk and this very interesting perspective that you gave on how science developed in the last several centuries and how the solar system objects contributed to this knowledge. Thank you very much. Unfortunately, we don't have the time to answer all the questions, but all of them are very interesting questions as well. I hope that we will have another time to answer those. Meanwhile, thank you very much. To the audience, there are many other events equally interesting happening in the next 10 days. Tomorrow, there is going to be a lecture on neutrino astronomy, the impossible dream of neutrino astronomy. While the astronomy that Mr. Madhusudan talked about was using light, now particles like neutrinos are now being used to observe distant objects. And Professor Basudas Gupta from TIFR is going to give a talk on the impossible dream of neutrino astronomy. So I hope to see all of you at 7 o'clock tomorrow evening. Thank you very much and have a good night.